Right, we're carrying on with question 1, part B. So we've drawn our nice table of results. Explain 2 ways in which you made sure the results were accurate when carrying out the investigation. And if you're not sure here, you can always go back to the instructions. Things like it tells you to use a white tile or a white sheet of paper when looking at the colours. That will make sure that the background doesn't interfere with the colour. So that I'm going to use that as my first point. And it says 2 ways, so we need 2 suggestions, and then it says explain, so we need to say why we're doing that. So my first suggestion is used a white tile to look at the cylinder colour. That means we can see the end point clearly and the background colours don't interfere. So that's my explanation. So to see the end point clearly, e.g. the background colours don't interfere. The mark scheme suggests that using the stopwatch to give results in milliseconds is a nice accurate way of running things. It's a very precise way of doing things, but I wouldn't necessarily, it's hard enough giving it to the nearest second an end point on this cylinder, so milliseconds is beyond what we need to do. So more useful things, if we're measuring some volumes here, so we need to get the volumes correctly. So like when we're measuring volumes and measuring cylinders, measuring the level at the bottom of the meniscus, and you've done that in your chemistry titrations. Reading things at eye level, that might be useful. I'm not going to go for those though, because I don't think the exact volume for these is that important, because we're using the concentrations, aren't we? I'm more interested in this last instruction where it says use a clean boiling tube each time. That sounds sensible, because there might be some of the previous concentration of acid or other contaminants in there. So I'm going to use that for my second suggestion. So used a clean boiling tube each time. And so the explanation, there's no contamination. For example, the previous acid concentration. And if I'm using 1 molar, I don't want any 0.5 molar acid previously in the tube, because it will lower that number from where I want it. Then we have a calculation, and it says calculate the average rate. Wow. A rate is always something per unit time, and you can see how we're working it out there in the unit, which is per second. Calculate the average rate of diffusion for each concentration of acid. Show your working. So it says show you working, so that's exactly what we're going to do. Write your answers in the table. Okay. So we're taking so if I just write these acid concentrations on the left, so we know what we're talking about, and the examiner can see which calculation you're doing. It says 1 over the average time, so 1 divided by the average time, 1076, and so the calculation is the same each time. 1 divided by 496, 1 divided by 460, 1 divided by 434. So we just need to put these into our calculator. So 1 divided by 1076 is an appallingly small number. So we've got 3 zeros, 9293. So just on this rough working out bit, I'm putting all the decimals in, and we can sort out what we want to do there. One divided by 595, 0.001686. 1 divided by 496, 0.002061. 1 divided by 460, 0.002179. 1 divided by 434, 0.00230441. So ideally you'd give these to the same significant figures in the answer table here. The mark scheme is actually allowing you to put more or less anything in here if you've worked it out correctly. But so I'm going to give these to two significant figures. So this 92 here, we're actually going to round that up to 93. That's what I'm going to put, because it might make it easier for me to plot later. So let's make sure how many zeros we got, and then 93, and then this is going to be 17, 0017. This is going to be 20, 0.0020. So two significant figures each time. That's going to be 22, 0.0022. This one's going to be 23, 0.0023. So I've done those to two significant figures, but actually it let you put whatever you needed in there. And already we can see a trend. The number is getting bigger as we go. So the rate of diffusion is going up with acid. And then there's a graph to draw with these horrendously small numbers, which I will do in the next video.